Greetings again from IIT Kanpur. So I'm back this time with a short historical perspective of how IC technology evolved and some future trends as well. So let's get started. First, of course, the disclaimer. So outline for this particular talk would be I would like to talk about some early efforts on doing what we think of about what electronic does today. Some early efforts what that was carried out and early electronics that was there. Then the coming of solid state device and integrated circuit. Following that, things stabilized and we will see what was the trend in IC world, a snapshot of it. And then finally, I'll conclude by talking about some alternate areas of semiconductor technology which also any student of traditional semiconductor technology should be aware of, and also see where things can be seamlessly integrated as well in the traditional electronics as well, the newer technologies in the traditional technology. So in view of that, I'll talk a little bit about some alternate areas. So let's get started. So first, it's the evolution of ICs. So ICs are integrated circuits. How did this circuit get into a small chip? How did it happen? And also, I must also make a clarification. Typically, when things about the IC industry or VLSI, we are talking about the digital electronics world. Okay, so here too, I would sort of emphasize on that because that's the backbone of the main industry. At least has become the backbone of main industry in the last many decades. So I'll give that idea, and then I would also try to hint about some niche semiconductor technologies as we go along, so that you are aware that there are other technologies available. So if you think about electronics, some of the first things that come to our mind is calculator. As a student, okay, that's okay, maybe I'm talking about my generation, but today's generation probably it's a smartphone, but whatever that may be, calculator is a simple electronic device, right? There were a lot of efforts for getting ways of doing calculations in a automated way rather than human effort. So one of the early efforts was by Charles Babbage, and in fact that's one of the closest that came to make a complete thing, although it was never built at that time. The patents were there, the ideas were all there, and if you look at it, this mechanical contraption would have cost 17,000 pounds. Just all that it will do is some addition, subtraction, and maybe multiplication. So it's mechanical, non-modular, standard parts are not available. It uses decimal. Modern electronics use binary whenever it has some computing. But some interesting ideas were there which still finds echo in today's technologies and today's approaches of design. And this was not completed at the time, 1832 or so, when the idea came up. Money was got, but it could not be completed because of many practical reasons. And somebody actually went ahead and built it in 1991, and they have made a sample of that, and it's located in the Science Museum in London. So clearly mechanical approach and some of the other approaches that were there was not conducive to what was being attempted, and certainly for the technology of that time. Maybe today it will be a different story. But so that being the effort to do something, but let's see, step back and see how electronics started off. It was in a lot of experiments were being done by physicists, a lot of new ideas, the electron was discovered and so on, a lot of ideas were coming up, and electricity itself was a fascinating subject. EM field theory, all that was being developed or had been developed. Around 1904, Fleming came up with a vacuum tube device which used to be used by a lot of physicists for doing experiments, and he found that he could build it to make it behave like a diode. That is, current will flow in one direction, in the opposite direction it won't. Okay, so this was in 1904. Following that, it didn't take much time. There were two electrodes which was behaving like a diode. Now here an intermediate electrode was introduced, and that was being biased, and then they found that they could amplify. And since it had 3 electrodes, it was called a triode, and this was in 1906. In some sense, you can say this is the birth of electronics. And once this was discovered, a lot of activity, especially radios and signals and all that, it started being used. It found a lot of use in those days. Telegraph, it was being used regularly. And these are the vacuum tubes that you see, and then this is how it would be when it is operational. Each of them will be glowing because they will be heated up. Filament will then emit electrons, and then if you reverse bias it, of course the electrons will be pushed away and the current will not be flowing. Now, this technology, while it was used for communications and various other amplifications of signals and all that, people were also trying to build other electronic gadgets, and this is an example of that. There are many. IBM 100, IBM 603, this is an electronic multiplier that they built in 1946. As you can see, all that it does is it multiplies, okay? And you can see the complexity of this whole circuit. And not just that, you find these vacuum tubes which you have to be very careful. It can break. If somebody hits with a hammer, it will break, right? So of course, the question is, why do you want to hit with a hammer? But by accident, something can happen, right? Then people even dreamt bigger, and they went ahead and actually built a so-called computer, ENIAC computer with vacuum tubes. And this particular computer used to occupy a huge room, okay, 80 feet by 8.5 feet high, and with a similar width. And this had 18,000 vacuum tubes. So this electronic numerical integrator and computer, ENIAC, one of its target was to find out what is the trajectory of a projectile, okay. I'm not sure how much it was used, and not just that, maintenance was very challenging, and they need a lot of power supply to keep it running. Often some wire will get nibbled by some rat or something, and they had a lot of challenges maintaining it. So this was the status of electronics. So some operations were going on, but it was not growing. The applications for general public was not as much. And there was a lot of effort to see whether we can go away from vacuum tube. And one of the efforts that really succeeded, remarkable success I would say, in 1948 in Bell Labs, it was reported, maybe sometime around that or before that, they must have actually done a lot of experiments related to that. So Bardeen and Breton, under the mentorship of Shockley, who was a manager, they ended up building something which on germanium, which showed characteristics of a bipolar junction transistor. So this was indeed revolutionary. And notice there was no vacuum tube here. It may look cumbersome based on the way we'll make devices today, but clearly it was solid state. Solid state means if you drop it, chances are it will not break, right? So it's not as fragile as the vacuum tube, and not just that, maintenance and all that was simply comes down. So this was the first attempt, and very soon people started making discrete devices. So this particular event, we can say, is the birth of modern solid state electronics. Remember that we often commemorate with a particular event, particular discovery, or particular patent getting published or paper getting published, but there's a lot of work that has been going on before it, around it, and so on. Now, for this work, they were awarded the Nobel Prize in 1956, rightly so. And soon people started packaging these things in very nice packets. And as I showed in the previous discussion, you could make packets like this. Of course, this is a microprocessor, but something discrete devices and all that they could make. So once they started doing that, they put it in a printed circuit board. Of course, not these chips, but these discrete components they were able to make. But in the late 50s and 60s, there was something else brewing. In late 50s, two groups led by Robert Noyce and Jack Kilby, they did something very interesting. Instead of making one device, one transistor on the chip, they went ahead and connected that on the chip right away. So what comes out is a complete circuit. You could not have access to the intermediate points, but you had the whole circuit as one block. This had a remarkable revolutionary effect because the reliability of the full circuit went up. The fact that you're making two devices right next to each other, you could actually make them very similar, almost identical in the real world, you can say. So that being the case, you could come up with newer ways of using that circuit, building newer circuits. So 741 that we know of, op-amp, is a good example of that. If you try to building with discrete devices, it will not be very efficient. You'll have a lot of losses and the gains will be poor and so on. Whereas, and even ideas like current mirrors and all could not be implemented in that. So once you put them together in a particular chip, the game changes. You are beginning to integrate stuff. Okay, integrating functions is a very important aspect of technology. We see that even in iPhones, one of the reasons, or the smartphones, one of the reasons they are so attractive is it integrates lots of things in one device, right? So here in the precursor in this electronic world, basic electronic world, integrated circuits was one of the first steps for integrating different components to make a more complex function. And this is an example of one of the things that was built not by them, but later in the 60s, one of the early ICs. Emitter coupled logic is what they have used in 1966. So in fact, this invention of the integrated circuit, while was known and was appreciated, but the value was not known sufficiently. So successful was it in the coming decades that in 2000, the Nobel Committee decided that this should be awarded Nobel Prize. And in the year 2000, Jack Kilby was awarded the Nobel Prize because Robert Noyce had already passed away. So usually Nobel Prize is not given to somebody who is not alive. So, but then they recognized that the whole electronic revolution had its that is, this integrated circuit had an important role in this whole electronic revolution. So we can say that the invention of the integrated circuit or reporting of this is the birth of the integrated circuit era. And once that was done, there was no stopping after that. So in the 70s, BJTs continued to rule. ECL and I2L technologies were one of the mainstays of BJTs. Then a parallel device was coming up. In fact, the device was invented in 1930s in terms of patents, but that was never demonstrated. That was the MOSFET. So the MOSFET technology, first it was PMOSFET, and then they decided to use NMOSFET because electrons had higher mobility. And NMOSFETs, once they were able to use and they were able to build inverters and digital circuits, in 2004, Intel came up with one of the classic microprocessors which used 2,300 transistors all in a single chip. And of course, microprocessors, once you build, you can do a lot. It has a lot of functionality, versatility. It can be applied in various places. It even becomes almost like a commodity product after that, because it can be used by itself in various applications. And then, of course, the trend that was started by this, it unleashed the floodgates, and almost for 50 years, we have seen this continuous development. More than 50 years now. So, and this is one of the later ones. You find that it has huge number of, the sophistication has becomes much more compared to this as it takes off. So this was in 74, this was the first one, 74, but subsequently they made more and more complicated device. So let us see how it all evolved. So this I'm just trying to show the timeline. Of course, I've already talked about BJT TTL logic. Around the same time, PMOSFET was making its entry to make circuits. PMOSFET is easier to make in terms of fabrication compared to BJT in some sense. Then BJT continued to rule. It was an established technology, but NMOSFET makes an appearance. It found its application in Intel's 4004. Around this time, people were saying, if PMOS is available, NMOS is available, why not combine them and make CMOS? It seems like a complex thing because a simple device is made complicated by putting two devices instead of one. But there was remarkable advantage because of that. The power consumption simply dropped. The static power consumption dropped. As a result, CMOS technology just took off. And it went on improving over the years. I'll talk about it in the subsequent lecture about scaling. Now, in between, a lot of new technologies made their appearance. Instead of using silicon, very first transistor was made in germanium. Following that, silicon slowly started finding acceptance because of the lot of advantages in terms of processing and how you handle it. Then silicon itself had some limitations, and silicon on insulator seemed to be one of the solutions. So in the 90s, especially mid 90s, some companies came up with some very high performance transistors, and that kept making the devices better, as well as we were able to shrink the devices. Then came newer ideas. Instead of having planar gates, why not fold the gates? So we had FinFETs. In the 2000s, it was late 90s, 2000s, it was invented, and then a little after that, Intel started using it, and then it has now become mainstream. And then in recent years, the device continues to get morphed, and now we have PMOS and NMOS right on top of each other, and this is called stacked FET. These are some of the latest devices that are being made. While that is true, the traditional device fabrication does continue in the background, may not be for the fastest devices, but for many other applications is used. But for the faster devices too, many times the language you use is the one that you derive from the traditional processing. So this continues to remain the mainstay of technology. Around this time, BiCMOS also came into play, because BJTs have an inherent advantage in terms of current gain and so on. So that's why many, even in our cell phone, some components are still BJTs. So BiCMOS is integrating bipolar and MOSFET on the same chip. That's not trivial, because they're two different technologies, but that has a lot of traction. And around 2000s, a lot of products also started coming out, and this is trudging along because this is very useful for high frequency applications. Then around first decade of the mid 2000s, we had newer materials emerge, and one of the materials that is remarkable is gallium nitride. Today it has a lot of applications, especially in power electronics as well as high speed circuits, and there's a whole ecosystem that is building up around gallium nitride and similar technologies. Newer technologies are coming up, and they have their own niche applications and implementations and technology roadmaps and so on. One is organic electronics, where you use organic semiconductors. You move away completely from silicon. You use carbon. So carbon-based technologies. Oxide electronics. Oxides traditionally were considered to be insulators, but by doing some things, you can actually use them for electronics. So these are some of the newer areas that is shaping up. These may not have that much of market as VLSI, silicon-based VLSI, but they are continuing to be important. And in the future, it looks like all these will come together in various forms, either on the same chip or within a package. That being said, newer ideas are in the horizon, and some of them are already taking off. Neuromorphic computing already is a lot of work is happening in this, although many of the methods of implementing it continues to be traditional silicon VLSI based technology, but soon newer ideas are bound to come using neuromorphic computing. And similarly, another amazing technology is quantum computing, and that's really has a lot of potential, but it's going to be sometime in the future. Now, we just saw how digital devices were progressing when I was talking about VLSI technology. I just want to sensitize that there are other semiconductor electronic areas which are also important. One of them, for example, is power electronics, silicon carbide, as I said, gallium nitride just some time back. These are some of the areas, and they have a lot of applications. In fact, modern cars are more electronics than mechanical, because there is so much of electronics in that. And especially now we are talking of self-driven cars and all that, there's bound to be a lot more electronics. And electric vehicles are, of course, there. They will require power electronics. So electric vehicles and all that are driving this technology. Then, of course, communications, that requires high speed. That's something that we have to also look at, and it is a totally different way of handling the processing. Certain other parameters become more important than what is there in traditional things. So for all these two, chips and hardware have to be built, and the general processing, of course, has some lot of commonality, but for each technology you specialize or emphasize on something else. A newer approach, we have large area or flexible electronics. In fact, display is one very important area. Your phone display, we all know that the phone displays kept going up and becoming more colorful and more pleasing. And similarly, we have television screens which are huge. So today we have generation 10.5, but you look at generation 8 itself. This is a huge television screen, and when you fabricate them, you have to do them in a monolithic manner, in a integrated manner. Similar concept to integrated circuits, but not but with its own nuances, and a totally different approach. You use glass, for example, as a substrate in many situations. Sometimes you use other novel plastics, etc. So this is another big technology, and it's a very little different from that, but with its own set of challenges which can be very difficult to solve. And then, of course, solar technology. We are talking about thicknesses of the solar devices of the order of tens of nanometers or hundreds of nanometers, or maybe even micron. But the area of the device is several meters sometimes, certainly 1 square meter, and if you look at a cumulative one, several square kilometers of solar is being deployed around the world, right? So this manufacturing has its own tricks, and in fact in India too, large area electronics based some industries are setting up. Cadmium telluride, I know there is a fab that is set up in Sriperumbudur. So there are many areas that are coming up. Then there are also novel applications like bio monitoring and healthcare and wearables. So and RFID tags, which I'm sure many of you must have seen nowadays. If you're going through a toll booth, many times RFID tags. So the way of manufacturing them will be slightly different, but they come with their own challenges. But the basic ideas still remain the same, how you approach them. That being said, it's true, electronics is wonderful, but there are lots of people who are also asking us to be cautious. One of the points that you should note is the amount of energy that is used, or the power dissipation that happens when you are running these technologies. Even an artificial intelligence search actually ends up consuming a lot of energy, because the transmission of data to computers around the world and search on computers around the world and so on. So it's very energy intensive, many of these operations. And even running a supercomputer itself is very energy intensive. In fact, you need very sophisticated cooling, and which is part of the reason they occupy huge spaces. Now, conventional electronics itself, there was a complaint that the power was going on increasing. But if you look at it, when artificial intelligence starts coming up, the projection is that it will become comparable to all the traditional electronics, just AI aspect of it. So clearly, this may not be tenable in the coming years. We don't know. We have to see how we are going to handle this. People are setting up dedicated power plants for AI-based computing. But it's good to wait for a moment and compare how Mother Nature tackles some of this. Of course, nature doesn't do exactly what we are trying to do, but nature also tries to do certain things. So if you look at the human brain, it just weighs 1.5 kilograms roughly, depending on the person, age, and things like that. Uses only about tens of watts, lower tens of watts. Its whole approach is different. It's not very precise, and in fact we have borrowed some of these ideas in some of our newer approaches like neuromorphic computing and so on, but that's the way nature works, right? And if you look at it, there was a supercomputer Roadrunner that was set up by IBM, and its one of the claims to fame was that it could plan how to cross a road and things like that. So if you look at the size of that, and this was a couple of decades, or more than a couple of decades ago, it was 227 metric tons, and 3 megawatt of power supply was needed for that supercomputer. So, and whereas even a squirrel will be able to cross a road, a cynic may say, I understand that what a computer does is very different from what a human often does, because, but then there are some things humans are able to do which a computer is still not able to do, right? So, of course, some frontiers are falling. They said computer could never defeat humans in chess. That has been that has come down. It has defeated chess champions. And then we are now having artificial intelligence where number of books are within quotes read and summary is being given. So it's amazing what all computers are doing. But at the same time, we all recognize that the humans in their own way, although a little error prone, are able to do certain things the computer we don't expect it to do. So clearly, we have to keep our eyes and ears open. First of all, sustainability, and will it be tenable? Will it be possible? What will happen to the environment, and also what would happen to the society as more and more electronics comes in? So this is one aspect one has to worry about. And besides that, are there other ways of doing stuff? And maybe this is where ideas like neuromorphic computing and quantum computing comes in. So the takeaways for this particular brief introduction, this is just an overview, a high 10,000 feet view of what it is. Initially, electronics were made by various methods. Mechanical was tried, then they went for vacuum tubes, and then there was a lot of success in, at least for amplification of signals and so on. And some products, small products, were being attempted. Vacuum tube radio is one thing that we all know. But then came solid state electronics with the invention of the transistor in Bell Labs. It was robust, it was economical, and a huge vacuum tube radio became the small handheld transistor. Even now, that's what is the name given to that small radio, right? As transistor, because it was using solid state devices in those days, transistors. And but that also was discrete. But once you put them all together and you are able to make complete systems and circuits and systems in a chip, the game changed. And then the integration really took off. And we will talk about that rate of growth of integration and all in the next lecture. So in the past 7 decades, since the beginning of transistors, nearly 7 decades are up, we have this integrated circuits have really taken us into a different world of electronics, and we are living in a very different world, both enabled and sometimes challenged by electronics, as we saw, because of the power consumption and so on. But certainly it has enabled and made life better for a lot more people over the decades. Now, that being said, we should also note that VLSI is one aspect. There are other things also have contributed to this, like power electronics, RF electronics, and so on. And also many new areas are emerging. And in the coming years, maybe we will take other alternative approaches. But clearly for the next foreseeable 2 to 3 decades, one can see that traditional VLSI processing based electronics will continue to play a very important role. And even if new ideas come, there will be an offshoot of that. That's what seems to be the trend. So given that, let us try and understand what is happening in the VLSI world in the coming lecture. Thank you.